In my spreadsheet, I did compare values, plotted them, and I did the top to bottom, by length and thickness, and then I did
The first problem I designed was the shape with the base of a right triangle and the cross sections of a semicircle. And I found the best way to model it was on Desmo, so I made, so that's the base looking down on it, which is a triangle. And then if you look at each cross section head on, it would look like that. And if you were to look at each cross section from the sides, it would be those black lines. Or if you would look at the cross sections from the top, it would be those black lines. So basically, imagine semicircles coming out of the paper, or out of the triangle upward. My spreadsheet, how I calculated volume was, let's see, my equation here was using the area of the cross section, which I got from taking the length of the circle, basically. And divided that by 2 to get the radius, squared that, multiplied by pi to get the area of that cross section, and then divided by 2 to get it to be a semicircle, so it wasn't an entire circle. And then I could get the volume over an interval by multiplying that by the thing, and then I took the volumes of 2 intervals and averaged them since the thing was going to be split between 2. So I got the volume of each cross section and added those together, and that gave me an approximate. Get the actual volume of it. I just took the integral. You can see there's the integral right there. I took the integral at the end, and there's nothing to subtract since it hit the origin and everything. So yeah, so I got the actual volume. And then just for fun, I made a margin of error, and there was only 0.5% of error between the approximate actual one. Which method is better? Obviously the more accurate one, because it was just one equation, and it was accurate. Yeah. Second graph I did was I modeled with hand. You can see the rest of the can there. Like, just imagine. That's the rest of it. The graph of the can was obviously there. To get the area, I just took the area in the middle of it and then multiplied that by, squared it, multiplied it by pi. Basically just take that cross section, spin it around, and that's how you can get the whole volume of it. It's the easiest way to do it. If I had to do it cross-section wise, I went piece by piece, and each of these represents basically the cross-sections in there, each of the equations. And I calculated the actual ones here, so you have x values where the cross-section is, the radius of it, the area of it, thickness of it, the average volume. In between them, add those up, you get the total volume, and then if you take the integral like I was saying before and just basically spin the length of it around, you get the actual volume. This margin of error was 8%, so it was a lot more, but yeah. So calculating the integral is easier and more accurate. Oh yeah, I also got each of the integrals and added them up since it was a piecewise function, because it wasn't just one, so I had to do that. close were your approximations? I already said that with the margin of error. What did I learn? It was really interesting to be able to visualize the shapes and then learn that the math lined up when you thought it would. Like if you spin this around, like multiply it by pi or something to get the area of a circle, and you already have one of the areas. And then you actually get the area, and it's just really cool to be able to visualize it and mathematically see that it's accurate. Yeah. Slightly over 5. Well, we took a little bit of a